All right, so far I have talked to you a lot about the types of plate boundaries, and even a fair amount about the connection that each of them have to volcanism, to seismicity, and even about the landforms that they tend to cause at the surface. But I still have not told you much about the rates at which those plates typically move. So geologically speaking, plates actually move really fast. Geologic rates, however, are much slower than human rates. So for us, fast motion would be something like 60 miles per hour, right? For humans, or say 100 kilometers per hour, which is pretty close to 60 miles per hour. But in geology, when we say that a process is taking place fast, we're speaking somewhere in the order of centimeters per year. Okay? So a much different scale. But in fact, actually most plates move even at a slower rate than that. Most of them only move a few millimeters per year. Every now and then you do find a fast moving plate that is going centimeters per year. So movement of these plates may not always be smooth and steady. It is very possible that it will happen by bouts. So for example, transform plate boundaries typically move this way. They will suddenly move a lot, say many centimeters or even meters, instantly, but this will happen only a few decades or centuries apart. So the average, when you take it year by year, is only going to be a few millimeters or centimeters per year. But it does not happen again continuously. It happens in larger events. So we get earthquakes when we have this displacement of many meters or several meters at a time. What happened, or maybe not necessarily meters, but on the larger scale. So what happens is that the stress built up from the friction of those two plates rubbing against one another, either again sideways or up and down if you have a convergent or divergent plate boundary type of deal. Once that friction is overcome, the energy is released in the form of a seismic wave. Or it happens when the two plates are spreading farther from one another and they are being partially stretched and torn apart, which also causes a release of energy in the form of seismic waves. Alright, so here is a short video that shows the transition of the western edge of North America in the last 40 million years or so. So let me show it to you real fast. Alright, so what you can see here is a continuous spreading center between the Pacific plate, right, and the Farallon plate, and later a spreading center between the Pacific plate and the Juan de Fuca plate, which is forming right there. Also in the north here you can see the subduction of the Farallon plate, which just happened, and the continuous, well, that one subducted fully, and the continuous subduction of the Juan de Fuca plate as it's moving more recently. So this would be close to 20 million years ago, as you're seeing there. You can also see that the northwest motion of the Pacific plate here, right, it's moving northwest, is starting to stretch the southern edge of the North American continent. So this is not part of the North American plate, what is being stretched out here. These Baja California and Southern California edges that are being stretched and moved towards the north are part of the Pacific plate. And so you see that what is happening is that eventually the southern part of California and Baja California are gonna keep moving, and eventually LA, oh sorry about that, let me show you there. So these are gonna keep moving, and eventually what's gonna happen is that basically LA is gonna appear right next to San Francisco. So, and even further, right, as they continue to move in that fashion. Another thing that is cool to point out is that you see the stretching of all of the states with the moving northwest. So you see, for example, Nevada is getting wider and wider, which causes the range and basin province. Same thing with Idaho, actually. We see that much of the, well, in this case, it's hard to see, but in this case, it's the eastern Snake River Plain, as well as the western Snake River Plain, are being stretched out, which also causes much of the mountain ranges that we see in the middle-ish southern part of the state. So the pioneers, the white clouds and whatnot, you see them as ranges, and then another basin, range, basin, Lost River Range, Lost River Basin, Lemhi Range, Lemhi Basin, so on and so forth. So pretty cool video. So in the next few slides here, we'll go through the evidence for the theory of plate tectonics and how we came about this evidence. So in the 1950s, as I said before, there was a lot of effort put into mapping of the ocean floor as technology had been developed for, and some of it was able to be developed for or post World War II. So there were a lot of tools at our reach to start mapping the many features that the ocean floor has. So by the mapping that was done, scientists at the time discovered features such as the mid-ocean ridges, as we've already talked about, right? Different sea mounts, as you're seeing here, for example, or island chains, ocean trenches, like the ones we had seen before as well, amongst other features that are within the ocean. So in the 1960s, it was Harry Hess who had enough observations that he dared to go ahead and suggest that there was something we call seafloor spreading. And the seafloor spreading, he believed, was the cause for continental drift, of which Alfred Wegener had talked about nearly half a century before, but who didn't have the right processes to make it happen. So Harry Hess suggested that seafloor spreading was going on based on three main things. The first thing, which in truth was really the reason for the second and the third thing, came about by the identification and the mapping of the oceanic ridges. So one of those ridges, namely the Mid-Atlantic Ridge, was especially useful to formulate this hypothesis that he had about seafloor spreading. So he noticed that the ridge itself fell almost exactly in the middle between South America and between Africa. So South America was nearly at the equal distance to the ridge itself as was Africa, but in the opposite direction. So if seafloor spreading did exist indeed, then perhaps these two continents were once one large landmass, as was suggested by Alfred Wegener a few decades before. Another line of evidence that Harry Hess used for his suggestion was the result from dating of volcanic rocks beneath the shallow sediment layer of the ocean floor. So, you know, the ocean is covered mostly by some amount of sediment that has been basically going through the ocean or the surface or near the surface and eventually settling down. However, a few meters only below that sediment layer, we find volcanic rocks. And so the dating of these volcanic rocks was one of those evidences that Harry Hess used in order to come up with his idea of seafloor spreading. So again, also in the 50s and 60s, a lot of effort was put into radiometric dating. So radiometric dating is a technique that dated minerals from the time of crystallization, meaning from the time that they went from being expressed as hot magma or lava and turned into solidified material, so turned into rock. So it was through this method of radioactive or simple regular isotopic decay dating that he was able to pinpoint the crystallization time for those minerals, and hence was able to pinpoint how old certain parts of the ocean were. So what they did is that they took rock samples at various locations. These locations were on either side of the mid-ocean ridges, right? But at equal distances. And they were able to find that the samples closest to the ridge were younger. So say that they took a sample here, they took a sample at the equal distance, but on the other side here. Then they took a sample here, and another sample at equal distance, but on the opposite side here. And what they saw again was that the samples that were closest to the ridge were youngest. And then as you got further from the ridge, those samples were getting older and older. So that is pretty much what you can see on the image itself. Here below you have a scale that says millions of years. So the red colors means that those are the youngest rocks. as you get further from red into yellow, green, and blue, those are going to be the oldest rocks per se that have been dated. So you see that these rocks that are the oldest are the furthest away from any of the ridges. These ones as well that are very far away from the ridge itself, right? So this image itself is super cool. We'll also talk about radiometric dating later in class as well for different purposes. So if it's not very clear, granted I didn't give you much of a overview about it. Don't worry too much about it. Just worry about the fact that they were able to date how old the rocks were at either side of the ridge, and that they found that again the youngest ones were closest to the ridge, and they got older and older the furthest away you get from the ridge. And the third line of evidence was the understanding and the mapping of paleomagnetic history of the ocean basins. So this is a bit more complicated to understand, but I'll go through it in the next few slides and try to explain it to you to the best of my abilities, okay? Alright, so here we'll start with some basics. So Earth's magnetic field has a north magnetic pole and a south magnetic pole. The magnetic field is caused by convection in the outer core, okay? So the outer core is what's causing the magnetic field, basically. Today, these magnetic poles roughly align with the geographic poles that are located where the Earth's rotational axis intersects the surface. So currently, the magnetic pole is near Labrador and Canada, and that is partly why when you're at different spots within east and west direction, you have to accommodate your compasses, because they don't all point towards true north, but they point towards magnetic north, which is again near the Labrador in Canada. So Earth's magnetic field is pretty similar to that which is produced by a simple bar magnet. So that is what you're seeing with the arrows, basically. Earth's magnetic field is also less obvious to us than the pull of gravity, for example, because we cannot actually feel that magnetic field. A movement of a compass needle, however, confirms that magnetic field's presence is there. But aside from this, some naturally occurring minerals that form on Earth when magma or when lava crystallize are indeed magnetic and are influenced by the Earth's magnetic field. Some of those minerals are things like magnetite and in occasions hematite. But magnetite, for example, hence the name magnetite, it's magnetic, is a mineral that is abundant in lava flows of basaltic composition, which are typically the type of lava flows that you experience at mid-ocean ridges. So, how that works is as the basaltic lava erupts at the surface, right, at the mid-ocean ridge, at temperatures that are greater than 1,000 degrees Celsius. So these temperatures are too high and exceed a threshold temperature for magnetism, meaning at this point magnetism isn't taking effect on the lava itself. So this threshold point, some of you might know, is called the Curie point. But what happens is that the magnetite mineral crystals in this molten lava are non-magnetic when the temperatures are that high, right? But as the lava starts to cool, these iron-rich minerals, or these iron-rich crystals, become magnetized and then align themselves parallel to the direction of the existing magnetic lines of force. So as they start to cool, the Curie point is no longer overcome, and so they do get magnetized and they align with the current lines of magnetic force. So once the minerals solidify and crystallize, they become rock. The magnetism that they possess usually remains frozen in that position. So that way is what will make them act like a compass needle, basically, because they will point to the position of the magnetic field at the time when they crystallized, when they formed. So overall, those rocks which formed thousands or even millions of years ago and contain some of this magnetite have a record of the direction of the magnetic poles at the time when the rocks actually crystallized and are said to possess this paleomagnetism.